So let's have a look at this question 4. We've been given the general formula for the binomial expansion here, and we're then applying it to this result, 1 minus x to the negative a half. Notice that we start at r equals 0 here rather than at r equals 1, so we will need to account for that a little bit later on. So what I'm going to do for part A is to start off by noting that we are using n equals negative a half, and of course we're replacing x by negative x. Now what I'm going to do is I'm not going to worry about the full summation. What I'm going to do is I'm going to look at this general term here. And if we can show that this general term can be written in this simplified format for this information here, then we've done exactly what we need to for part A. So let's sub in this information here into the general binomial expansion. So our general term becomes n, which is negative a half. Negative a half minus 1 is negative 3 over 2, and then you get negative 5 over 2 and all the numbers that have that pattern, and then you have negative a half minus r plus 1 all over, and rather than 1 times 2 times all the numbers up to r, let's write the denominator as r factorial, and multiplied by, instead of x, we've got negative x to the r. So I'm not writing out all of the terms of this summation, I'm writing out the general term, and what I want to do is aim to show that this general term can be simplified to this format here. So next, I'm going to start simplifying this. So look at that numerator. Each of these terms contributes a factor of negative 1, and there are r of these products in the numerator. So that means I can take out negative 1 and raise it to the power r, because that's the same as negative 1 multiplied by itself r times. Now that means that all of these terms then become positive. So we have a half, 3 over 2, 5 over 2, dot, 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 all the way up to, and this one here, we're going to essentially give it all a common denominator of 2. So remember that it's going to become positive as well, so it will simplify to 2r minus 1 over 2. Remember, the negative was taken out to be part of negative 1 to the power of r. We've then got this term here, which I'm going to rewrite as negative 1 to the power of r x to the power of r. So splitting negative x up into negative 1 times x, and then raising each part separately to the power of r. This is all over a denominator of r factorial. Now let's start simplifying. So look at the numerator, we have this and this. Now these two would multiply together to give us negative 1 to the power of 2r, which is just going to be 1. Now what I'm going to do with all these fractions is I'm going to keep their numerators in the overall numerator, so 1 multiplied by 3 multiplied by 5 multiplied by all the way up to and including 2r minus 1. And we have an x to the r as well in the numerator, and then in the denominator, all of these will contribute 2 times 2 times 2 all the way up to here. And remember, there are r terms, there are r products in the numerator, so that's a factor of 2 to the power of r, which we bring into the denominator, and of course there's already a factor of r factorial existing in the denominator. Now, what next? Well, look at this part here, the negative 1 to the power of 2 to the power of r. Well, that could be written as negative 1 to the power of 2 to the power of r, so it just simplifies down to 1, so we can ignore that. Now the next bit is really very clever, because I'm going to rewrite this blue product here, 1 times 3 times 5 times all the way up to 2r. I'm going to write it as 1 multiplied by 2 multiplied by 3 multiplied by 4 multiplied by 5 multiplied by all the way up to, and then we've got 2r minus 1, and then multiplied by the next term along, which would be 2r if we're going consecutively, all multiplied by x to the r, all over. Now in the denominator originally we had 2 to the r multiplied by r factorial, which was there originally, but to cancel out all these terms we have now included in the product in the numerator, I'm going to need in the denominator 2 multiplied by 4 multiplied by 6 multiplied by all the even numbers up to and including 2r. Now the red parts will cancel, and that leaves us with something that's identical to the line above. So this is a perfectly legal manoeuvre, and it's a very clever little bit of maths that you can do involving factorials. Now we're still not there. Now let's look at the numerator. We now have here 1 times 2 times 3 times 4 times 5 all the way up to 2r. So this is the same as 2r all factorial. Now that's good, because look at my question here, part A. In the first part of the summation, I've got 2r, choose r. So that's going to involve a 2r factorial. So this is good. I'm heading in the right direction. Multiplied by x to the power r. Now in my denominator, I then have for this part here 2 to the r times r factorial, which is just there. Now this red part here, let's look at rewriting it, because we've got 2 multiplied by 1, multiplied by 2, multiplied by 2, there's your 4, multiplied by 2, multiplied by 3, multiplied by all the way up to the end, 2 multiplied by r. Now, we can then rewrite that denominator. Let's put in the numerator first of all. So let's put in everything we already have, 2 to the r times r factorial. That denominator, look at the fact that you've got a 2 times a 2 times a 2 times a 2 all the way up to the end. Well, that is 2 multiplied by itself r times, that is 2 to the power r, and then the rest of that is simply 1 multiplied by 2 multiplied by 3 all the way up to r, so it's an r factorial. So what happens now? Well, we have 2r overall factorial over r factorial multiplied by r factorial multiplied by x to the r over. Now, look at these two. We have 2 to the r multiplied by 2 to the r. Well, what does that give us? 2 to the r multiplied by 2 to the r is the same as 2 to the 2r, adding the indices, which is 2 to the 2 to the r, which is 4 to the power of r. And then we pretty much have done it really, because this part here, let me highlight it so we can see, what's this equivalent to? Well, that is equivalent to 2r choose r, which is, if you remember, n factorial over r factorial n minus r factorial, if you use the formula for calculating a factorial. So that's 2r all factorial over r factorial r factorial. So this is equal to 2r choose r, which can be written almost a bit like a vector. 2r choose r, and then the second part just needs to be written like that. X over 4, and then all raised to the power of r. So because we've shown that the general term simplifies to this result here, we've done everything we needed to. The only thing that we really need to do in addition to this is to check what happens for r equals 0, because this summation here starts at r equals 0, and in the original binomial expansion you've got a term of 1. So what we're hoping for is when we substitute r equals 0 into the general term, we get a result of 1, and that allows us to start this summation from 0, because it will include the term that is just equal to 1. So if r equals 0, then I've got 2r choose r, which is 0 choose 0, which equals 1, multiplied by x over 4 to the power of r, which is also 0, so multiplied by 1, because anything to the power of 0 apart from 0 is 1. So we get 1. So the general term works for r equals 0 as well. So part B, we need to use this general result that they've given us here and apply that to this result here. Now, you've done this in your binomial expansions work. We need to rewrite 9 minus 4x squared to the power of negative a half. So I'm going to take out the 9, 1 minus 4/9 x squared, the whole thing raised to the power of negative half. So of course this becomes a third, 1 minus 4 ninths x squared to the negative a half. So we've now written this roughly in this format here, the 1 minus being the crucial part. Now our n value is still negative a half, so that's good. But x, of course, is going to be replaced by 4 ninths x squared. We don't need to worry about the negative sign because that's accounted for here. So it doesn't matter that, in fact, it's good that we've got a negative here because it matches our question. So here's what we need to do. We need to substitute into this part here and show that we get this result here effectively. So let me start writing this out. So 9 minus 4x squared to the negative a half can be written as 1/3 1 minus 4 ninths x squared to the power of negative a half, which is 1/3 of the sum between r equals 0 and infinity of 2r choose r. I'm using the green highlighted result. Now, instead of x over 4, I've got 4 ninths x squared over 4, all to the power of r. So I've substituted into the green result. I now need to simplify and show I get down to this. So it's going to be some very simple algebra. As you can see, the 2r choose r part stays the same. Now, over here, this becomes x squared over 9 to the power of r. The answer has 3's in it rather than 9's, so we're going to rewrite this. So the numerator of this can become x to the power of 2r. Now the denominator, of course, 9 is equal to 3 squared, so we've got 3 squared to the power of r, or 3 to the power of 2r. So let's bring this factor of 1/3 inside the summation. So that's 1 over 3 multiplied by x to the 2r over 3 to the 2r. So this then becomes x to the 2r over 3 to the 2r plus 1. Now, the question had 3 to the power of q in its format, and we had to state q in terms of r, so it's clear q is equal to 2r plus 1. Now, part C then requires us to use what we have done so far in some interesting way. Now, this is where it really requires you to think a little bit more critically about how to get from one step to another. Now, you'll notice here that this looks very similar to this, but starts at r equals 1. We have a 2r over 9 in this part here, and then the power of this is 2r minus 1, which is less than this by 1. Where do you see that concept? You're multiplying by the power, you're reducing a power by 1, it's differentiation. So this, which I'm highlighting in yellow, is the derivative of this. So can we show that though? That's what we've got to be able to do. So what we're going to do is we're going to differentiate this. Now, what are you actually differentiating? You're differentiating a series. Let's just write in, that was 3 to the power of 2r plus 1. Let's just get that correct. What are you actually differentiating? You're differentiating a series, which means you're differentiating an infinite sum of terms. Now, all you would be doing, in theory, is writing out that sum of terms and then differentiating them one by one. You're allowed to do that because this is a convergent series. How do you know it's convergent? You're given this information up here. So that means we're allowed to differentiate over the summation. So we don't have to differentiate it term by term. We can differentiate the general term, and that will give us the result. So this is then going to equal... Now, actually, let's think about this carefully, because If we work out the term when r equals 0, we know that's equal to 1, so we can actually just rewrite this like that. Just starting the summation at 1 and taking out the term where r equals 0. Now, we're differentiating, so of course that will differentiate to give us 0. So we now only need to worry about this, and remember, in the question, what we're looking for starts with r equals 1, so we want our summation to start with r equals 1 as well. So differentiating with respect to x. So we need to multiply by the power, which is 2r, reduce the power by 1, so it becomes x to the 2r minus 1, and then this is all over 3 to the power of 2r plus 1. Now look at what we're aiming for over here, and you can see we've got the x to the 2r minus 1, but they've got a 3 to the 2r minus 1. So we're going to adjust this. So I'm going to leave my x to the 2r minus 1, but that denominator here, so this, I'm going to rewrite that as 3 to the 2r minus 1 multiplied by 3 squared. Add the indices and you can see we get back to what we had previously. So this is good because that 3 squared gives me a factor of 9 in the denominator, so I can then write 2r over 9 for this part here, and then for the last part I can just take x over 3 and raise that all to the power of 2r minus 1. So it's an equivalent statement. So what we know is, or what we've discovered, is that this is equal to d by dx of this summation here. We've just shown it to be true. So that means it must be equivalent to what you get when you differentiate what this sum is actually equal to. Now we know what this sum is actually equal to. It's equal to this result here, because remember that can be written in this form there. So this is the same as differentiating 9 minus 4x squared to the power of negative a half. So let's multiply by the power, negative a half, reduce the power by 1, so negative 3 over 2, multiply by the derivative of the inner function. So I'm basically just using the chain rule very quickly here, and this then simplifies to give me 4x over 9 minus 4x squared to the power of 3 over 2. I'll bring that into the denominator. And this is the answer. That's the exact value of this summation. Now the last part here, you can see they're just asking you to make use of what we've got here, and the fact that we have just identified that this is equal to 4x over 9 minus 4x squared, or to the power of 3 over 2. So look at the two in comparison with each other, and what's changed? Well, we've got this root 5 here, which is new, and then this over here. Now comparing the two, that root 5 times 1 over 5 to the r must be equivalent to this. So what we're going to do is set them equal to each other and find the value of x, and then substitute it into the right hand side, i.e. into this. So let's start by looking at those green parts which I've highlighted. So x over 3 to the power of 2r minus 1 must be equal to root 5 multiplied by 1 over 5 to the power of r. So x to the 2r minus 1 over 3 to the 2r minus 1 must be equal to, well, we've got 5 to the power of a half, and then we are dividing by 5 to the r, so 5 to the half take away r, we can write it like that. So x to the 2r minus 1 is equal to 3 to the 2r minus 1 multiplied by 5 to the half take away r. Now, we need to know what x is, but it's quite difficult to look at this on both sides when some of the powers are different. It's very helpful here that these powers are the same. So what I'm going to do is leave this part alone here, and I'm going to rewrite this part over here as 5 to the power of, now I want it to have a power of 2r minus 1, but what I'm going to do is put a factor of -1/2 here, so when you expand the bracket it returns to being a half take away r. Now where do I go from here? Well, I can rewrite this as 3 to the power of 2r minus 1 multiplied by 5 to the -1/2 to the power of 2r minus 1. Remember, power of a power means multiply. So this is 3 to the 2r minus 1. Now what is 5 to the power of -1/2? Well, it's 1 over root 5. So I have this, and then this can all be written as 3 over root 5 raised to the power of 2r minus 1. So both numerator and denominator would be raised to the 2r minus 1. And of course, because this is equal to x to the 2r minus 1, we can now conclude from here that x has got to equal 3 over root 5. Now, what do I do with that value of x? Well, I substitute it into here. So this is 4 multiplied by 3 over root 5 multiplied by, now think of it as multiplied by 1 over 9 minus 4 multiplied by x squared, which is 9 over 5 to the power of 3 over 2. Now let's simplify this. So I've got 4 multiplied by 3 over root 5 multiplied by 1 over 9 to the 3 over 2, 1 take away 4/5 to the 3 over 2, bit of factorisation here. So that is 4 multiplied by 3 over root 5 times 1 over, now 9 to the 3 over 2 is 27, so this is a 27 in the denominator. And then here, this is interesting, we've got 1/5 to the power of 3 over 2. That starts to look quite complicated when you have a fraction within a fraction here. So we'll think about that in a second. Run out of space here. Let's clear just a little bit of space over there for me to work. So that's 4 multiplied by 3 over, now this root 5 I'll write as 5 to the power of 1/2 multiplied by 1 over 27 multiplied by 1 over, now 1/5 to the power of 3 over 2, well 1/5 is 5 to the -1, so I can write that as 5 to the power of -3 over 2. And then hopefully you can see the cancellation that will result here. So we have 1 and 9 there. So we've got a 4 in the numerator and 9 in the denominator. And then we end up with 1 over 5 to the -1 in the denominator here. But of course that just becomes 5 in the numerator. So the answer, and I'm sorry it's squeezed in the corner here, is 20 over 9.